Experiencing the awesome powers associated with a lightning strike makes us aware of the importance of electromagnetism in our world. Not just in our external world, but also internally, where electromagnetism controls the biochemistry of our physiology. It is interesting to learn that a complete theory of electromagnetism was already completed by James Clerk Maxwell about 150 years ago. This theory still stands today, and it is as important as it was 150 years ago. Electromagnetism also drives our modern technology that we have come used to. The scanning electron micrograph and the schematic sketch underneath illustrate such a modern device. In this case, two silicon quantum dots, a pair of quantum dots identified as dot 1 and dot 2 in panel B, and underneath the 7 aluminium electrodes are controlled via electromagnetic fields. The fields are created by charging the electrodes in a certain way, and they have to permeate the various materials involved in constructing this device. The materials include conductors, insulators, and semiconductors. The semiconductor silicon in light blue in panel B is the base of the device, and the silicon dioxide and the oxidized aluminium act as insulators. In particular, the oxidized aluminium separates the 7 electrodes from each other so that they don't shorten. Ultimately, these devices are designed to permit quantum computing, which might have future applications in cryptography. These particular images are from a paper by an Australian group led by Lai, published in 2011 in Scientific Reports. It is clear that such a device can only be designed and operated based on a complete understanding of electromagnetism and how it interacts with quantum mechanics. All materials that we know can be assigned to one of 3 classes: conductor, insulator, or semiconductor. It may be noted that this device features all 3 classes: silicon, a semiconductor, silicon dioxide, oxidized aluminium as insulators, and the gates are made of aluminium, which is a conductor. The 2 regions indicated in red in panel B have been doped with phosphorus. This makes them N-type. A semiconductor and its functionality can be modified by doping, which means adding small amounts of an impurity, for example, phosphorus or boron. The doping can achieve N-type or P-type character. The functionality of the semiconductor, as represented by its conductivity, can be drastically changed by doping. Whereas the characteristics of conductors and insulators cannot be changed much, the behavior of semiconductors in such modern devices can be drastically changed. This is at the heart of modern electronics. The quantum dots dot 1 and dot 2 are actually tiny regions of nanometer dimension with increased electron density, with these additional electrons drawn there due to the fields that are applied by the electrodes above. All materials can be identified according to their electrical properties as either being a conductor, a semiconductor, or an insulator. Copper is shown here, silicon, and then silica, quartz, silicon dioxide, which is an insulator. Semiconductors are called intrinsic when they are as pure as possible without barely any impurities. However, they can also be N-type or P-type. That depends on the amount of doping, the amount of impurities introduced, and the impurities can either make the semiconductor excessive in positive charges or excessive in negative charges. P-types means excessive in positive charges, and N-type means there is an excess of negative charge carriers in the semiconductor. The most important entities that microscopically carry the charges and therefore create the electromagnetic fields are the electrons. There are other microscopic particles such as protons, positrons, or muons that carry charges. However, electrons are the most important among those. Because they are such tiny particles, in fact we consider them just as a point without a physical dimension, they experience quantum effects. and the consideration of quantum physics is important when designing electromagnetic devices at a very small scale. The so-called classical description of electromagnetism, based on the four postulated Maxwell equations, is predominantly concerned with the macroscopic world, where the dimensions are large and many electrons contribute to an electric current. Under those circumstances, quantum effects can be safely neglected. This course discusses the concepts and the structure of the four postulated Maxwell equations that underpin classical electromagnetism. The photo on the left shows a beam of electrons. The electrons travel in a gas at a very low pressure, ionizing the gas molecules. The beam of electrons is forced onto a circular trajectory by an external magnetic field. A section of one of the electromagnetic coils, painted red, can be made out behind the glass bulb. Traditionally, we depict electrons as a circle with a minus sign inside. This identifies a certain location for that electron and the fact that this particle is negatively charged. It may be noted that while this depiction is quite useful in discussing electromagnetism at the macroscopic scale, it is microscopically not correct because the electron is a point, and in fact a location cannot really be defined because of its quantum mechanical wave-like behavior. At school, the physics of electricity and magnetism is typically introduced as a collection of experimental facts that are explained by laws of physics. This more advanced course develops the mathematical structure that underpins the physics of electromagnetism that is observed. This is achieved through the introduction of fundamental postulated axioms, from which the experimental physical laws can then be derived. In the case of classical electromagnetism, the postulates are the four Maxwell equations. They are such assumed axioms that to date have not been contradicted. These equations were first suggested in a more complex notation in 1865 by James Clerk Maxwell, and they found their modern form in 1884 through work by Heaviside, Willard, and Hertz. Postulates, axioms, are tenets of general validity, which are accepted rather than being derived or demonstrated. Familiar other postulated axioms are, for example, Newton's law and the four fundamental laws of thermodynamics. Whereas the formulation of postulated laws in words is generally possible, the use of differential equations, as for example with Newton's second law as well, is frequent in physics. A discussion of these four postulated Maxwell equations, the axioms of electromagnetism, is central to this course. An axiom or a postulate is a statement that is considered to be correct. Such a correct statement tends to be chosen to be of very general nature to permit deductions that lead to an explanation of special cases. The words come from the Greek axioma and the Latin postulatus. The postulated Maxwell equations, which stand at the beginning of the Maxwell theory of electromagnetism, are three-dimensional, time-dependent differential equations. The four differential equations relate to four important electromagnetic fields and are formulated using vector calculus. The two important differential del operators are the curl and the divergence operator. In particular, it is postulated that the divergence of D, the electric flux density, is always equal to the charge density. Secondly, it is postulated that the divergence B, the magnetic flux density, is always equal to zero. Thirdly, the curl of the electric field strength is always equal to the negative time differential of the magnetic flux density B. And finally, the curl of the magnetic field strength is equal to the sum of the electric current density J plus the time differential of the electric flux density. We see that in these four equations there are four electromagnetic fields, the D, B, E, and H field. all four fields are vector fields. In addition to that, we have the scalar electric charge density ρ in the first postulate and the vectorial current density J in the fourth postulate. Each of the four postulates relates to an experimental law. The first equation relates to Gauss's law and also to Coulomb's law, Coulomb's force law. F equals 1 over 4 pi epsilon naught times Q1, Q2 divided by the distance squared. The second law is an expression of Gauss's law of magnetostatics. The third equation relates to Faraday's induction law, and the fourth equation has its equivalent in Ampere's sequital law and contains a theoretical Maxwell addition. This addition is important to make the last two equations self-consistent and allow for the explanation of electromagnetic waves. As indicated on the right, the divergence and curl operators can also be expressed using the del operator as del dot and del cross respectively. An understanding of all aspects of the Maxwell equations requires familiarity with the following concepts and mathematical operations: the field concept and the four electromagnetic fields D, E, B, and H, printed in bold here to indicate that there are vector fields. D, electric flux density, E, electric field strength, B, magnetic flux density, and H, magnetic field strength. Secondly, the concept of current density J, which is also a vector, and current I, which is a scalar. The use and meaning of divergence, the operator divergence, and the use and meaning of curl, the curl operator. Furthermore, the consequences of partial time differentiations of fields, and the fact that the postulates 3 and 4, the last two equations, are linked, that they are coupled due to the Maxwell addition, which allows for the repetition of field changes in time and space, which in particular explains electromagnetic waves. The task is considerable, and students often grapple with the three-dimensional nature of the problem, which requires familiarity with vector calculus and the skill of three-dimensional visualization. Furthermore, due to the time dependence, all four fields and both charge and current density depend on both, not just position but also on time. Due to the time dependence, the situation is not static but can be changing. This is very complicated. The four differential Maxwell postulates can also be represented as integral equations, shown here. The two types of mathematical expressions, differential equations on one side and integral equations on the other side, are completely equivalent and can be transformed into one and another by using two mathematical equations known as the Gauss divergence theorem and Stokes' theorem. The integral form of Gauss's law, at the top here, is often introduced in introductory studies of electromagnetism and relates to Coulomb's law. The differential forms of Maxwell's equations impress with their concise notation. In contrast, the integral forms are more convoluted, featuring closed integrals on the left-hand side. However, they are much more convenient in typical problem-solving exercises. Without wanting to go into detail at this stage, let me point out that the closed surface and path integrals on the left-hand side of these four equations equal volume and surface integrals on the right-hand side. Faraday's law and Ampere's law also feature time differentiations on the right-hand side. If the two surface integrations are carried out, in the case of Faraday's law, this integral equals the negative total differential of the magnetic flux, and in the case of Ampere's law, the integration equals the sum of current and the time differentiation of the electric flux. Flux is here expressed as a capital Phi symbol. Independent of differential or integral form, the last two Maxwell equations contain both an electric field and a magnetic field. One of these fields is differentiated with respect to time. If the field is time independent, if the situation is static, this gives zero. With dB dt equals 0 and dd dt equals 0, the Maxwell equations decouple, and two sets of equations are obtained, one defining electrostatics and the other set defining magnetostatics. In the case of electrostatics, we read that the divergence of the electric flux density, which is now not dependent on time but only on position r, equals the charge density, also only dependent on position. This is Gauss's law of electrostatics. Furthermore, the curl of electric field strength is equal to 0. In the case of magnetostatics, divergence of B equals 0, and the curl of the magnetic field strength H is equal to the vectorial current density J. The first of these two equations, div B equals 0, is Gauss's law of magnetostatics. The decoupling thus provides two independent sets of two postulates each, with the first set defining electrostatics and the second set defining magnetostatics. These two important fields, electric field on one side and magnetic field on the other side, can thus be discussed completely separately, greatly simplifying comprehension. The fact that the Maxwell equations can be decoupled, as just discussed, is the reason why electromagnetism is typically presented in the way illustrated on this slide. At first, the theory is discussed in vacuum, starting with electrostatics. This is typically followed by a discussion of magnetostatics, which has a very similar mathematical structure to electrostatics. In the next step, the coupling of the electric to the magnetic field is included in the theory. This permits a discussion of phenomena and technologies such as induction, motors and generators. Finally, it is shown that the coupling of the electric and magnetic field predicts the electromagnetic wave equation. The solution of this wave equation are electromagnetic waves. Once electromagnetic theory is understood in vacuum, the discussion of this theory can be detailed further by considering phenomena that apply in matter. To a student, the considerable amount of mathematics in either the differential or the integral form of the Maxwell equations may be daunting. Looking at the original paper by James Clerk Maxwell from 1865, of which I'm showing here just the first paragraph, it becomes, however, immediately apparent that these four equations reduce the complexity of electromagnetism, which Maxwell describes in his paper in great detail and with much more complicated mathematics, to a form that is simple and symmetric. This is in particular achieved through the use of vector calculus. A student, therefore, has to have a firm knowledge of vector calculus to understand electromagnetism.